Okay, let's dive right into this. When we look out at the field of crops or even just stare at the dirt in our own backyard, it's incredibly easy to think of soil as just static ground, right? Just dirt. But beneath our feet lies a totally hidden, microscopic world that dictates exactly how that ground behaves. Welcome to this explainer, where we are going to demystify what we call the invisible engines of the Earth, soil colloids.
To really wrap our heads around this hidden world, we're going to trace a logical path straight from the micro level all the way to the macro. We'll quickly hit on 1. What are soil colloids? 2. Form and massive scale. 3. The magnetic soil. 4. Soil in motion. 5. The microscopic dance. And finally, 6. Building better soil.
All right, let's jump straight into section 1. What exactly are soil colloids?
The term itself actually has a pretty fascinating origin story. It was coined way back in 1861 by Thomas Graham. He combined the Greek word kolla, which means glue, with eidos, which means like. So literally, it translates to glue-like. By scientific definition, a colloidal solution is a dispersion where the particle diameters range from about 10 to 2,000 angstroms. To put that in perspective, we're talking 0.0001 to 0.2 microns. In the soil system, certain particles fall exactly into this incredibly tiny size range, and they exhibit these unique, glue-like properties. But to really grasp just how small that is, let's compare it to a couple things we already know.
So the crucial point here is that soil colloids sit perfectly in this sort of magic middle ground between two extremes. On one side, you have a true solution, think sugar or salt dissolved in water. There, the particles are just single molecules or ions. They are incredibly tiny, less than 0.001 microns. But then, on the other hand, you have a suspension, like if you stirred sand into water. Those particles are huge aggregates made of millions of molecules, sizing up at over 2,000 angstroms. Colloids bridge that gap. They're small enough to actually stay suspended, but large enough to have some absolutely powerful chemical and physical impacts on the soil.
Moving right along to section 2, form and massive scale. Let's see what these actually look like.
Generally, soil colloids are broadly classified as inorganic and organic. The inorganic ones, the mineral colloids, actually have very specific distinct shapes. They will be called laminated. This means they are made up of layers of plates, or flakes, or even rods, and they develop far more along their horizontal axis than their vertical one. For example, kaolinite forms these neat hexagonal crystals. Montmorillonite forms flakes. Halloysite takes on a rod shape. Meanwhile, your organic colloids, like humus, have a totally variable shape. But regardless of the specific shape, the edges of these particles can be clean-cut, frayed, or fluffy. And that becomes absolutely vital when we start talking about their surface area.
And speaking of surface area, just look at this number for a second. 700,000 square kilometers. That is massive. Because colloids are so incredibly small, again, generally under 1 micron, they expose a wildly disproportionate surface area per unit of mass. The external surface of just 1 gram of clay colloid is at least 1,000 times greater than 1 single gram of sand. But wait, it doesn't even stop there. Certain silicate clays have plate-like structures that offer internal surfaces inside the particle as well. So if you take the upper 15 centimeters of just 1 single hectare of clay soil, the total internal and external surface area could literally equal 700,000 square kilometers. It's an almost incomprehensible amount of surface area packed into one tiny plot of land.
Which brings us nicely to section 3, the magnetic soil, because opposites really do attract.
Now, what's really interesting about this slide is the consequence of all that surface area we just talked about. These colloidal surfaces, both the internal and external ones, characteristically carry electrical charges. For most colloids, electronegative charge is predominant. And since opposites attract, these negatively charged soil colloids act like powerful microscopic magnets. They attract hundreds of thousands of positively charged ions, known as cations. This dynamic creates what scientists call an ionic double layer, and it's of massive practical significance for exactly how soil holds onto nutrients in water.
The actual process of these colloids grabbing onto cations in water is called adsorption. But they don't just grab things randomly. Actually, scratch that. It's the exact opposite of random. It is governed by 3 strict rules based on the ion type, its concentration, and the colloid itself. Rule number 1. The higher the valency of the ion, the higher the adsorption. The only exception here is the hydrogen ion. Rule number 2.
If you have two ions with the exact same valency, the colloid prefers the one with the higher atomic weight. And rule 3, the concentration of the ion in the soil solution directly determines the rate of adsorption. So it's this highly regulated, complex chemical sorting process, happening millions of times a second right in the dirt.
Let's look at how this chemical superpower plays out physically in Section 4, Soil in Motion.
The combined lubricating and binding influence of that adsorbed water leads to a physical property called plasticity. That's basically the capability of the soil being molded. And this quote brilliantly illustrates the concept. Particles easily slide over each other, much like panes of glass with films of water between them. If a given soil has more than about 15% clay, this plate-like nature of the particles makes it incredibly pliable. And this is a big deal, because it directly influences just how difficult or how easy tillage operations are going to be for farmers out in the field.
But it goes way beyond just plasticity. That adsorbed water causes a whole chain reaction of other physical movements. For starters, we see swelling when clays get wet. This is primarily due to intercrystal expansion and entrapped air pushing things apart. Then, when those same clays go through a prolonged dry period, we see severe shrinkage. This leaves soils that are rich in smectite minerals crisscrossed by these wide, deep cracks. Initially, those cracks let rain penetrate rapidly, sure. But as swelling starts up again, the soil closes right back up and becomes highly impermeable. And finally, there's cohesion. Hydrogen bonding between the clay's surfaces and the water molecules creates a super strong attractive force, practically gluing the clay particles together to form resistant, hard clods.
Let's shift gears now to Section 5, the microscopic dance.
When you actually have a colloid suspension, you have to realize that these particles are never still. They are under constant rapid motion. This is called Brownian movement, and it was defined by Robert Brown back in 1927. It's a continuous, rapid, zigzag movement. The tiny colloidal particles dart in short, straight lines and then change their path abruptly because they are literally colliding with other colloidal particles or the molecules of the dispersion medium itself. The smaller the particle, the faster it moves, and the more often it collides. And here's the kicker. These constant, rapid collisions are actually the main driver responsible for the coagulation or flocculation of soil particles.
Now, because they are so small, you normally can't even see colloidal suspensions with the naked eye, but we can perceive them thanks to something called the Tyndall effect. A really great relatable example of this is dust particles floating in the air. That's a colloidal suspension right there. If you pass a strong beam of light through it, the colloidal-sized particles diffuse the light. This diffusion essentially makes the microscopic particles appear way bigger than their original size. It quite literally makes the invisible visible.
And that brings us to our final point, Section 6, Building Better Soil. Let's see how all of this builds into massive agricultural impact.
So, we've seen how clay particles naturally carry a negative charge, and therefore want to repel each other and disperse. But when those negative charges are satisfied by tightly held cations, the repulsive forces drop, and the particles clump together. This clumping is what we call flocculation. From an agricultural standpoint, flocculation is generally fantastic. It's highly beneficial because it's the very first step in forming stable granules in the soil structure. On the exact opposite side of the spectrum, we have deflocculation. This is the harmful dispersion of particles. It happens when highly hydrated monovalent cations like sodium ions associate with the particles. Sodium is just too loosely held and doesn't effectively reduce the electronegativity, causing the particles to continuously repel each other. They act entirely independently, and it absolutely destroys the soil structure.
So, what do we do if a field is suffering from deflocculation and dispersion because of too much sodium? How do we fix it? Well, the source outlines 3 precise steps to reduce this harmful dispersion and save the soil structure. Step 1, decrease the pH of the medium. Step 2, aggressively replace that harmful sodium with stronger, tighter holding cations, specifically hydrogen, calcium, magnesium, and aluminum. And Step 3, increase the overall salt concentration in the soil solution.
Understanding soil isn't just about digging in the dirt. It's about mastering the microscopic interactions of colloids, from their massive surface areas and their electronegativity to their constant zigzagging collisions. It all comes down to managing this delicate balance of ions, which leaves us with this pretty crucial question to consider. If highly hydrated sodium ions can literally disperse and destroy our soil's structural integrity, are we really doing enough to actively balance the complex colloidal chemistry right beneath our feet? Thank you for joining me for this explainer on the invisible engines of the Earth. Keep exploring, and I'll catch you next time.